Welcome to part 5 of the nuclear physics series. In this video we're going to be looking at radioactive decay in the form of beta decay. Now if you remember from 2 videos ago, we looked at the fact that beta decay can occur as positive beta decay but also as negative beta decay. We said that the negative beta particle is essentially an electron. And if we write it in the form of the nucleons that we're talking about, we know that the electron has no nucleon mass because it's not a nucleon. But it does have this -1 charge, which would correspond to the proton charge of 1. Now, this positive beta particle that we talked about is known as a positron. And the positron has the exact same no nucleon mass, but it does have a positive charge. So it's essentially an electron with a positive charge. Now what we see happen in beta decay, let's take a look at negative beta decay first. What we see happen is that this beta particle was not in the nucleus preceding the reaction. It is the result of the reaction. So it's not like a trapped electron inside the nucleus that's released through this process. And so what is proposed is that a neutron, which we can have a nucleon mass of 1 and no charge, actually breaks down into a proton, which has a 1 nucleon mass, the same as a neutron, and a 1 charge. And this is going to balance very well then because we have these forms. Now it wasn't first discovered when beta decay was discovered, but there was an energy issue in this reaction. And so what was found to occur was this almost massless particle known as an antineutrino, which is symbolized with this sign. So if we wanted to write an actual nuclear reaction now, we could say that if I have element X with mass number A, atomic number Z, it can undergo beta decay, in this case negative beta decay, because the beta particle is 0 here. It's going to maintain its same atomic mass, but its atomic number will add +1 because I have this extra proton here. And then I'm going to show that I have the beta particle and the antineutrino. So let's do an example here. Let's pick out, let's say thorium-234. Now thorium-234, we know thorium has a atomic number of 90, and what's going to happen is the mass number should stay the same, but we need to add 1, so we're going to add it to 90, which will give us 91, and we have our beta particle, negative beta particle, and our antineutrino. And the element that is 91 is actually protactinium, which is symbol Pa. So we see this here as the negative beta decay. Now we could also have positive beta decay, which is positron decay. And this does occur actually in quite a lot more cases than you would think, never having probably heard of one. And what we see here is that a proton that is in the midst of the nucleus, so this can't happen with a lone proton, because the proton has less mass than a neutron, but the proton seems to be able to give rise to a neutron and a positive beta particle, or a positron, and instead of an antineutrino, a neutrino to balance it all out. So aluminum-26 is a radioactive isotope, so let's go ahead and try to work this one out. So aluminum-26 is going to decay into something that still has the mass number 26, but now should have a 1 less number for its atomic number, which is 12, because that value is over here now with the positive beta particle. And so what we're going to see happen in this case is that we're going to be left with element 12, which is magnesium. And we're of course going to have our positron, or our positive beta particle, and our neutrino. And this happens fairly commonly. So if we want to write a a generic statement like we did over here. Remember that this is the statement for negative beta decay. What we find for positive beta decay is that we should have element X with atomic mass A, atomic number Z, will break down into another element that still has the same atomic mass, but will have one less atomic number, and then we need to account for the positron and the neutrino. Now the last form I'm going to include here in this video is gamma decay. In gamma decay, it's going to be probably the easiest of all, which is why it's not going to have its own video. We're going to have element X, atomic mass A, atomic number Z, and we're going to put a little asterisk here to represent the fact that it's in an excited state. So this means that there's extra energy involved here that wouldn't ordinarily be there. And you can think of something like the excited state where an electron's at a higher energy level, even though it's still not yet ionized. So this is in an excited state, and when gamma decay occurs, we get this same exact element because the gamma particle, which we symbolize with the Greek letter gamma, has no mass and no charge. And so it's purely just a gamma ray emission. And that gamma ray emission, that energy that's released, can be determined by using one of the photon equations. And this can actually occur fairly commonly. Now, what will cause something to undergo beta versus gamma versus alpha decay? Well, there's actually a lot of different factors involved. But one thing that's very interesting is that the Earth's core actually undergoes a lot of these spontaneous alpha, beta, and gamma decays, and that's what creates the conduction and convection within the Earth's mantle. If these things didn't happen, if we didn't have radioactive elements, we would have the problem of really a cooling down mantle, and that would create a lot of other problems with the heating of the Earth. Now we're going to take a look here. Our last example is going to be an example where we have alpha and beta decay that can occur in a sample. Now keep in mind, each sample that is decaying, we've only looked at one atom at a time, so it can happen where we're going to have multiple things going on at the same time. So let's look at bismuth 211. Bismuth 211, bismuth has a atomic number 83, and what we see happen is alpha decay. So let's practice that. So we have our alpha particle, the helium nucleus. So we're going to have 211 minus 4, which will give me 207, 83 minus 2, which will give me 81. And if I look up what element 81 is, it's actually thallium, which is Ti. Now, additionally, at the same time, the bismuth can undergo negative beta decay. So we start with the same isotope of bismuth, 211, and what's going to happen is it's going to break down by negative beta decay. So we're going to keep the same atomic number, but this number is going to increase and go up to 84. And we should then have our negative beta particle and our antineutrino. And if we look at what element 84 is, that's actually going to be polonium. And so we can see that in a sample of bismuth 211, you can actually get polonium out of it as well as thallium, with alpha and negative beta particles being emitted at the same time.